In this video, I illustrate how to utilize this factor program. It's online as a free download, and it's really pretty cool because one of the things that it allows you to do is to generate a polychord correlation matrix and use that as input in your factor analysis. So basically, the reason why this is useful is because when you are running a factor analysis, you are pivoting off of the correlations among a set of measured variables. And so traditional factor analytic techniques will assume that your measured variables are continuous and essentially falling at an interval or ratio level of measurement. However, what do you do if you happen to have a situation where your measured variables are ordinal in scale? One thought might be to take your measured variables and generate something like through SPSS, something like a correlation matrix of Spearman correlations or Kendall's tau correlations. The problem with this particular approach is that those procedures are assuming that the variables are ordinal, and it basically violates the assumptions related to the factor analytic procedure, which is that, again, you have continuous variables. So using a matrix of correlations among ordinal variables as they are originally scaled can be problematic. So one way around this problem is to generate a matrix of polychord correlations, which essentially involves trying to discover or figure out those latent variables that are behind the scenes in terms of producing the ranks on your measured variables. So polychord correlation is essentially the correlation between the latent variables that are producing the relationship between your measured variables. So that's essentially what a polychord correlation does for you. And so essentially then if we generate a matrix of polychord correlations, and then we can carry out the factor analysis, because essentially those latent variables are assumed to be continuous, and then you are essentially meeting the assumptions related to the standard factor analytic procedures. So you don't have that option in SPSS. So so the only options that you have in terms of correlation matrices and running the factor analysis basically involves assuming that you have Pearson's correlations reflecting the relationship between measured variables that are already continuous. But if your variables are ordinal, you don't have that option. So what I'm going to do is illustrate how you can run a factor analysis using a polychord correlation matrix through this program right here. And the cool thing is that this factor program integrates the construction of the polychord correlation matrix with the factor procedure. So if you are generating a polychord correlation matrix through other programs, a lot of times you have to do that first and then input it into the factor analysis component in order to generate a factor solution. But the nice thing about this program is that it does this all for you. The one hiccup or hitch is just that you have to utilize a DAT file instead of anything like a standard SPSS or Stata file. But obtaining those particular files is not really that big of a headache. So here's a set of data. I've got essentially I have data on 198 cases. You can see that there are a few missing cases here and there. There's a missing case or missing value on this variable here. There's a missing value and so forth. But basically we have 198 cases with 16 variables. And so basically what I have to do is first convert this data into a DAT file. So the way that you can do this, if you just go to File, Save As, and where, this is the file that I'm using right here, and so I'm just going to use the little drop-down menu, go to tab delimited DAT file, and so you can see it changes the extension here to DAT, and save it. And so now I have in my data set, in my on my drive, I now have a DAT file. So as you can see right here, this is what we just created. So this is going to be used as input into the other program. So at this point, that's really all I have to worry about with respect to SPSS. And so now I'm going to go to this program. So what I have to do, though, is to actually download the program. So I'm going to click on free download, and the version of Windows that I have, I'm just going to click on download the factor for 64-bit Windows. So I'm going to click on this. And so as you can see down here, the download is basically the program or application downloads into the zip file here. So I'm going to open this up, and so there's my factor program. So I can actually save it to a desktop, or I could save it to my drive if I want. I could just copy it and put it on my little drive here if I want, or whatever. And so, you can see it right here. I've downloaded it here. So, if I want to open it up, then I can just, click on it, and there you go. Like I said, you could either save it to your desktop, or you can save it to your disk, or whatever. But so now I have a copy of it. And so, at this point, what I need to do is I need to read the data in and configure my analysis. So I'll click on Read Data. And so right here where it says number of participants, I'm going to type in 198, because that's how many cases were in the original SPSS file. It was 198 cases, and we had 16 measured variables. So if we can imagine, these were items on a survey, Likert items, scaled 1 to 7. So in this case right here, I'll just say there's 16 measured variables. And under participant scores, this is where I find the DAT file. So here I'll click on this polychoric matrix DAT file that I just generated a couple of minutes ago. And if you have any missing value codes, you'll put the number here. I think the default is just 999, but if that's not the missing value code that you have in your original data set, and what will ultimately be in the data file, the DAT file, then then you can change that. But really, what's going to happen is there will just be missing data in this data file for those cases where there's a missing data point on a given variable. So now I'm going to click on OK, and you'll see that what pops up is this little warning message. This is just saying that for row number 88, that's case number 88, there's only 15 values. So basically, out of the 16 variables, there's a missing value on the variable. So the row is dropped in all subsequent analyses and so forth. So and it'll be the same for a couple of these. So if you happen to have missing data in your data set, this basically what this is doing is performing a listwise deletion for you. If there's no missing data, then you would not be getting those warnings. So there's nothing horribly wrong or anything like that associated with seeing that. It's just that that's what it means. So next, you'll click on Configure Analysis, and you've got your variables that are included, and if you had any variables that you didn't want to include in the analysis, you can move them over here. So the next step is you click on the polychoric tetrachoric correlation. So it's giving you a lowest possible item score and a highest item score here. And the procedure for determining the number of factors or components, if you're doing a components analysis, the default is parallel analysis, and I tend to like that the most. So let me just kind of highlight that even though this SPSS file is up here, right here, this is just in the background. This is the actual program that we're working with. So at any rate, So let's say I want to run a principal components analysis on these items right here. So I would click on principal components analysis with the polychoric correlation checked off, and if I want to establish a rotation of some sort, there's a little drop down menu, so you've got different rotation options as well. So let's say I wanted to ask for let's see if I can find it here, a Promax rotation. It's in here. Normalized Promax, something that basically if you ask for a Promax through SPSS, that's what you'll get. So I can click on this right here. Now what you'll have to do is to specify the number of factors or components to extract, and basically I had 16 measured variables, and if I and basically, you know, if I put something like you know, I want 16 components to extract, what you'll see if you click on OK is you'll get this little message right here. It says at least 3 variables for each factor or component should be included in the analysis. So basically the maximum number of components or factors can easily be obtained just by just taking the number of items and dividing by 3. And so I'll just do that, which gives me 5.33. So you can't type 5.33 into the box here. So what you'll have to do is, and so you can see that the error comes up here. So basically, I'm just going to highlight this and just put 5 as the maximum. So at this point, now when I click on OK, it goes about it's ready to go. And so now I'll click on compute, and you have this nice little indicator here that basically is just saying, hey, we're processing your data. Let me get that off of there. So, you know, keep in mind it takes a few, it may take a minute or two for the processing to finish, but there it is. And so the output shows up in a text file, or excuse me, in basically a notebook or notepad. And so essentially you can see the details of the analysis, and basically as you scroll down, you'll see that we have essentially you know, a description, basically some indicators or descriptions of the ordinal variables in terms of the frequency counts for each value on your variable. So these are those. So you can see some of these distributions are kind of skewed, but you know, again, we're dealing with ordinal data here. When we scroll down, you can see now this right here, this contains the polychoric correlations among your measured variables. So so then down below you've got the adequacy of the correlation matrix for factoring. So you've got the Kaiser-Meyer-Olkin test. Basically you're looking for values that are at least above 0.7. In the 0.7s you're talking about fair or adequate. Above 0.7 you're talking about, you know, good and very good. So they actually include a nice little descriptor here just to say it's fair matrix for factoring. You've got Bartlett's statistic right here, which is a significance test, and so basically if this test is statistically significant, then it's appropriate to carry out the factor analysis. So next we have the explained variance based on the eigenvalues. So you can see in this first column right here, first 2 columns actually, it's giving you all 16 factors that have been extracted, and you know, we had essentially, so these are the eigenvalues for those, excuse me, not factors, components. So these are the eigenvalues for all 16 components, as well as the proportion of variance in the measured variables is accounted for by those components. And then over here in the cumulative proportion of variance, this is the cumulative percentage or proportion accounted for by those 5 components that we had requested. So next you have the parallel analysis based on the principal components analysis, and this is just comparing the randomly generated eigenvalues against the eigenvalues from your data. So these eigenvalues in this column, this real data eigenvalues are the same ones that you see up here. And you have essentially you have the mean of the randomly generated correlation matrix, or the mean eigenvalues from those randomly generated correlation matrices for all 16 components, as well as the 95th percentile. And essentially what you're doing is you are looking to see at what point the randomly generated eigenvalues exceed the eigenvalues from your real data, and at that point you essentially retain those components that with the real data eigenvalues that are greater than the random eigenvalues. So they actually give you an advised number of dimensions, which is 3. So they're actually suggesting that a 3-component solution is appropriate, because you can see right here, here's your eigenvalue from your real data. Your 95th percentile is lower. The eigenvalue for the second component, you can see again the random eigenvalue is lower, and then for the third component, it's the real data eigenvalue is greater than the 95th percentile. But when you move to the fourth component, you can see that this eigenvalue is actually less than the randomly generated eigenvalue. So it actually suggests a 3-component solution. So at this point, I probably will go about the business of reanalyzing the data and forcing a 3-component solution. So I would go to Configure Analysis, request 3 components, and so after that, then it would make a little bit more sense to then interpret any kind of rotated component solution. So I'm going to click on OK and then compute again. And so now I get to wait a few minutes until this factoring procedure is completed. Okay, so you can see here, again, this is from our, you can see the number of components is 3, which is what we had requested. We have a lot of the same details that we had before. In this case right here, here's our polyquark matrix again, and KMO, Bartlett's, those are obviously the same as what they were before. And then you have the cumulative proportions that are reflecting the 3 components that we've essentially decided to retain. So at this point there's not really much in the way of a need to look at the parallel analysis anymore, because this is just the same information we had. So then we scroll down, we have the unrotated loading matrix. So this is pre-rotation in terms and basically this is a structure matrix. It's the correlations between each of our measured variables. So these were the items from the scale and the components that we retained. You also have the communalities for each of the measured variables as well, which is the proportion of variation in the measured variables accounted for by those components that were retained in the analysis. Then we have the rotated loading matrix. So this is essentially rotating those component axes, and these are again correlations between each of our measured variables, or the items from our scale, and the components. And so we would use those correlations in order to name those components. The program's kind of cool in that it actually, by default, it gives you this little rotated loading matrix, and it says loadings lower than an absolute value of 0.30 are omitted. So it's a way of sort of cleaning things up a little bit and making it a little bit easier to read. So basically all of this information is replayed down here, except for those loadings that we had up here that didn't where they were less than 0.30. So and then when we scroll down, we also have the explained variance and reliability of the rotated components. So you can see right here that we have components 1, 2, and 3, and so at any rate, again, these are just the components and the variance accounted for, proportion of variance and reliability estimates. So the next thing that I'll show you really quickly here is, let's say I want to carry out a standard factor analysis. So I'll go to Configure Analysis, and here I'll leave the polyquark correlations alone. And in this particular case, if I want basically a common factor analysis, I'm interested in explaining the intercorrelations among the measured variables, whereas principal components is focused on explaining all of the variation in the set of measured variables. So the option I can adopt is the unweighted least squares for the factor analysis process. Let's just go back and we'll use 5 as the default for the number of factors to extract, and I'll just leave everything else the way it was. So I'll click on OK, and then compute, and so we'll wait a couple minutes here. Okay, so here is the output from that factor analysis. So I'm going to scroll down, and again, you can see that we have our information about the polychoric matrix, the Bartlett's KMO test. The explained variance that you see right here, all this is basically a components solution. This is basically the initial process of the factoring, or the factoring process, and then eventually the eigenvalues are actually, or the eigenvalues from the reduced correlation matrix is presented below. So you can see you have the eigenvalues for each of the factors. So as you can see, it involves basically our output still has a parallel analysis involved, and in terms of the advised numbers of dimensions, it's suggesting a two-factor solution might best represent the pattern of intercorrelations among our measured variables. So what I'll do is I'll just go back and under configure, and I'll just type in a 2 to force a two-factor solution. So I'm going to click on OK, and then compute, and we'll wait for the solution again. So here's our two-factor solution that we've requested, and so when we scroll down, you can see that we have our basic information as before. Again, these are eigenvalues from a initial components analysis. So this is essentially the analysis on the full correlation matrix and then the two-factor solution, but that's not really what we're interested in. We're interested in the final solution from the reduced matrix. So these are the eigenvalues from that factor process. So when we scroll down, we have our unrotated loading matrix. So these are pre-rotation of the factors, and you have the communalities associated with each of the measured variables or items from our survey. And then we also have the rotated loading matrix, which again are just basically correlations between each of the measured variables and the factors that we have retained. And so this is where the this sort of cleans up what we have right up here and helps us to better interpret the pattern of loadings. You also have down here, you've got the explained variance and reliability of the rotated factors. So you've got essentially the eigenvalues for each of the factors, rotated factors, as well as you also have reliability estimates right here. So one final thing that I want to mention is that we were using Promax rotation. If you wanted to use a different type of rotational strategy, let's say for instance I want to use Promax. I'll just use the normalized Promax here, and click on OK. And basically, when we this is just to generate a rotation where the rotated factors are allowed to correlate. So with Promax rotation, it's an orthogonal rotational strategy where basically the factors are not allowed to correlate. So what that means in terms of the output is that you'll get both the structure matrix as well as a pattern matrix, and then also a matrix of the intercorrelations among your factors. So here's the output now with using the Promax rotation, so everything else will look pretty much the same as what we've just talked about with respect to the two-factor solution. But when we come down here, now we get again, here's the unrotated loading matrix. When we scroll down a little bit more, you'll see that we have a structure matrix, and these are the zero-order correlations between each of the measured variables, or the items in this particular illustration, and the two factors. So this would be interpreted the same way that we would interpret the matrix of rotated loadings following the Promax rotation. But the thing is that when you allow for when you utilize a rotational strategy like Promax, you're allowing for there to be an intercorrelation among the factors. And so you'll see right here you've got the interfactors correlation matrix. So this is the correlation in our data between factor 1 and factor 2. So it happens to be a 0.146. So that's not a very high correlation, but it is a correlation nonetheless. And when you scroll up here, you can see you've got the rotated loading matrix, and this is basically what's called a pattern matrix. And so so basically the loadings are reflecting the relationship between each of the measured variables and the factors, controlling for the correlation between the factors. So they're sort of analogous to standardized regression coefficients from that standpoint. So at any rate, we still have down here we have the rotated loading matrix, which is set to basically not show you those loadings that are less than 0.30 for our pattern matrix. And so then you can interpret the results from this matrix up here a little easier down here. So that basically highlights some details on using this factor analysis program. I actually like it. I think it's a pretty cool program, and certainly is a little easier to use than some of the other programs where you're having to work with the polychoric matrix directly. So at any rate, check this out. This is the site where you can download the program. So hope this was a helpful demonstration for you.